podcast is brought to you by LMU Munich.
Very much. Well, first of all, like the other speakers, I would like to thank Dieter and his fellow members of the committee for inviting me to this conference. Beautiful surroundings. Secondly, I would also like to thank them for assigning me this task, which is a very special challenge in front of this audience. Oops. And thirdly, I would like to thank my AI colleagues, Dario Benedetti and Daniele Oriti, for updating me on some of the recent developments in this subject. And I hope very much that what you're going to hear from me is not too much of a distortion of what they told me. So on Monday, we heard about non-elephant biology, and you might think this is something similar. I realize that many people will not like this terminology because it's not good to define something by what it is not. But I would like to say that at this time we have I think everyone agrees that we have no universally accepted theory of quantum gravity. And I think in this situation it's very important to keep one's mind and one's eyes open about other possibilities and other ideas, even if they run against some deep-seated beliefs. And as you can see, the popular media are paying quite some attention to these developments. Now, the divide of the quantum gravity community can be traced back to a basic fact that you all know, and to the question of how to deal with it. Namely, the fact that perturbative quantum gravity is non-renormalizable. What you see here is the famous two-loop counterterm that was computed by Goroff, Sagnoli, and Van de Ven. And the question is, what conclusions do you draw from the existence of this non-renormalizable divergence? Now, coming from a particle physics community, the first conclusion would seem to be completely obvious. And if you have in mind the history and development of the standard model and unification, namely that a consistent quantization of gravity requires a radical modification of Einstein's theory at short distances, and in particular, the inclusion of supersymmetric matter, fermions, and fermions in the supersymmetric form, so as to take care of the divergences and to somehow use these fermions to cancel infinities. However, a general relativist may take a somewhat different view on this, because in general relativity, the most important thing about general Einstein's theory is not that it is a theory of massless spin-2 particles, but it is the geometry and the features like general covariance and so on that are really should be put in the foreground. And this point of view has been most pointedly expressed by Roger Penrose, who refers to this procedure of perturbation theory as steamrollering the beauty of Einstein's theory into flatness and linearity. And there he goes on to say that you cannot expect, after having done such a brutal thing to this beautiful theory, to, by some magic, recover its beauty in a quantized form. So in this context, then you would be led to speculate maybe there's some other way to take care of these ultraviolet divergences, and that these are really artifacts of the perturbative treatment, and that they might actually disappear upon a proper to be defined, proper non-perturbative quantization of Einstein's theory. Now, independently of these points of view, I think everyone should agree that no proposed theory of quantum gravity can claim complete success that does not somehow explain the ultimate fate of this divergence, be it by cancellation, removal, like in strings here, by going from point-like to extended objects, or by some other mechanism, and this mechanism has to be exhibited in all detail. And I would also like to remind you that the real problem here is not only the infinities, because you could decide perhaps to subtract them off order by order, but the fact that when you do this, you run into infinitely many ambiguities, because you will have to fix infinitely many constant parameters to make any kind of prediction. And therefore, there's also a complete loss of predictivity if you adopt this point of view. And as you will see at the end, I think I will get back to this point. I think this is also a problem for the non-perturbative approaches. So if you follow this second line of reasoning, the question is, can properly quantized general relativity, Einstein's theory, stand on its own feet as a quantum theory of gravity? Or expressed differently, is there an alternative to the particle physics stratagem of looking for mechanisms to cancel or remove the ultraviolet infinities of the perturbatively quantized theory, which is usually done by introducing a whole enormous superstructure of extra dimensions, supersymmetry, relativistic extended objects, infinite towers of massive states, infinite component field theory, D-branes, and so on? Or is it enough to stick with the basic features of general relativity, namely general covariance, background independence, and the fact that we live in 4 dimensions, in order to arrive at a quantization of geometry, a consistent quantization of geometry and space-time? And the other question, of course, not mentioned here is it really necessary to unify the fundamental interactions with gravity in order to achieve this goal? And in fact, most of these alternative approaches put the question of unification aside and try to discuss the problem, in first approximation at least, within the context of gravity. So here's a partial list of these approaches, starting with the famous Wheeler-DeWitt program of canonically quantizing gravity. The Wheeler-DeWitt equation is now roughly 50 years old. And then the path integral approach, Euclidean, Lorentzian. I would also mention matrix models in this context. Then there's this new approach, loop quantum gravity, and the various discrete approaches, non-commutative geometry, the idea of asymptotic safety, RG fixed points, emergent quantum gravity, and then you can get even more abstract by throwing away even more of what you know and trying to start completely from scratch with, this is something called causal set theory, or maybe even cellular automata. I think it was Tove who first had this kind of idea. Now, I will not simply, I decided not simply to go through this catalog and give you a kind of micro view of all the things that are being done, because all of these are now very active fields. There are many people working on this, there are many ideas, many proposals, but rather to concentrate on a few features, and I've actually picked the topics that I'm somewhat more familiar with. And I would like, the main intention of this talk is not to inform you about all kinds of details, but about the ideas and motivations that drive people doing these approaches. I should also say that I will not say anything about black hole entropy. Maybe you've seen Ashok Sen's papers of a few weeks ago, but Ashok is here, so you can ask him questions that are related to this. So I will concentrate on asymptotic safety and then discuss, first of all, loop quantum gravity, and then the further developments that came out of this loop quantum gravity program. So here's a list of certainly very incomplete and biased list of reviews for each of these. So some of these people are the pioneers of these approaches, and I would also like to mention our own review, of which takes a more critical view of these developments of 7 years ago. And more recently, there was also a review by Alexandrov and Roche, which is even more detailed, discusses this subject in even more detail. So the first point I would like to discuss is this asymptotic safety program, which was originally proposed by Weinberg in 79, and they took quite a few years before people returned to this idea, and I think it was in this form restarted by Martin Reuter in 95. I want to discuss this approach first, or this idea first, because first of all, it is closest in spirit to conventional quantum field theory ideas like RG flow, RG group, and so on. And furthermore, this idea has no problem connecting this ansatz to semi-classical gravity. So there's no problem in somehow recovering the classical Einstein equations from it. Equally important, I think, and that's actually my main reason for discussing this first, is the following. If any of the non-perturbative approaches succeeds, the description of the resulting low energy theory via an effective, something like an effective action, of which the Einstein-Hilbert action is one part, will probably reduce to this. Now when I write here succeeds, I mean not only that you succeed in constructing some theory, but success also includes somehow explaining how the classical Einstein theory and the classical space-time continuum emerge out of this proposed theory. And as I said, in this context, it's hard for me to imagine any other explanation to dispose of the two-loop divergence than this idea. Now, the approach pretends to be agnostic about the microscopic theory, which is in some sense, everyone doing this non-perturbative approaches somehow thinks about this as being related to asymptotic safety. So all the relevant information here is in the universality classes of the RG flows. Now, when I say pretends to be agnostic, then it's not completely true, because somehow underlying this approach is the assumption that actually space and time can be understood as a continuum even below the Planck scale. Most approaches to quantum gravity somehow suppose that something dramatic happens at the Planck scale or Planck lengths, but here basically, at least as a working hypothesis, that you assume that you can work with just in the usual framework of quantum field theory, which lives on a continuum spacetime. Now you might ask, well, if I have RG flows, why don't I see anything running if I look outside? Because we know that Newton's constant to very large distance, and looking back in time is just a constant. It doesn't run. But the idea here is somehow, in terms of analogy, you should think of the Planck mass as being analogous as to lambda QCD, in the sense that this is the lower end of the asymptotic scaling regime. So the scaling only starts above the Planck scale. So that also means that observable effects of any kind can arise only if some prediction can be made about the infrared limit as the theory flows down from the asymptotically safe fixed point. Such a prediction could be, for example, the statement that the cosmological constant is non-zero and assumes a certain value. So what are the basic assumptions here? Well, the assumption are as follows. The first assumption is that the ultraviolet limit of gravity is determined by a non-Gaussian fixed point of the gravitational renormalization group flow, and that this fixed point controls the behavior of the theory at high energies and renders physical quantities safe from unphysical divergences. And secondly, there's an extra assumption that this fixed point belongs to UV critical hypersurface of finite dimension within the infinite dimensional space of gravitational couplings, higher order couplings. And this is in some sense essential. If you just had a fixed point somewhere in this infinite dimensional space and no such critical hypersurface, then you would essentially run the same problem as perturbatively renormalized gravity, in the sense that you would have to fix an infinite number of parameters. So this assumption somehow says that you have to replace the notion of conventional notion of renormalizability by a weaker notion, in the sense that you have to fix a few parameters, but it's still a finite number of parameters that needs to be fixed. The aim then is to construct a scale-dependent effective action, gamma, and k is the scale parameter, which is such that when you take k to infinity, you recover the bare action. This need not be the Einstein-Hilbert action, but it could be something that has higher order corrections, or almost for sure has higher order corrections. And when you flow to low momenta, you cover the effective low energy action. And the dynamical information about the theory is not in the flow equation, but in the initial conditions. So some have to test various initial conditions, work out the equations, and see where they flow to. Right. So the evidence for this program was first presented by Weinberg, was based on 1 over epsilon expansion using dimensional regularization. There have been various arguments, also 1 over n expansions and even perturbation theory. But nowadays, most people use, for the analysis, use these functional renormalization group equation, which grew out of, well, this came first in statistical physics, and then in flat space quantum field theory. It was first formulated by Polchinski in '84. Later, there was a modification or improvement by Christoph Wetterich. But this equation, in the form that it's now used for the gravity case, was formulated by Reuter in 1998. So the equation is this. So here you have this effective action, which depends on the scale, and you also put in a cutoff parameter. But let me say right away that in doing these things, you simply assume that you somehow can remove the cutoff and simply study the equation independently, or simply putting this equal to infinity. So that's an assumption, of course. Now, the crucial new feature of this equation, as opposed to the earlier equations, that this doesn't take in place in flat space, but it's a theory of gravity, and therefore you have to deal with the question of gauge invariant, diffeomorphism invariance, and so on. And the way this has been solved, a proposed solution here, is by doing a kind of background splitting. You split the full metric into a background metric plus a small fluctuation, and then you require this effective action to be background covariant, where here you have just a diffeomorphism with respect to the background, and then you treat this perturbation as a kind of spin-2 field in this background. So this is a functional differential equation, and one piece here, so it's the function itself. You take the derivative here with respect to the scale parameter. Yes, there's a functional derivative, so there's a functional trace with respect to this fluctuation. But in addition, you need this cutoff function, which is required to sort of make you integrate out the modes between k and lambda, or k and infinity. And I think this idea was first introduced by Polchinski. Now, so this means that the cutoff scale, the problem here being, and the necessity of this split can be seen as follows. If you want to measure, if you want to introduce a scale, you need some kind of metric to measure it. But if the metric itself is part of the dynamics, that's kind of hard to describe. And therefore, this split is also essential in order to introduce a scale. So here's a metric, background metric, and then you can measure this cutoff scale as well as the eigenmodes and the eigenvalues with respect to this background metric. So this is an essential ingredient of this. And then once you succeed in solving this equation somehow, then the final effective action is simply obtained by putting h equals 0. Now, as I said, it does not appear that gamma k, if it do not do this split by itself, can obey a covariant, generally covariant renormalization group equation. Now, another interesting feature is here that once you succeed in doing this, suppose you can define such a scale-dependent effective action, then you can also derive something like, in a self-consistent way, like a scale-dependent metric, by simply solving the equations, the differential equations, or the Einstein equations, or the generalization really for this k-dependent action. So you recover from this a metric that itself becomes scale dependent. So what is the evidence? And this was that's the work that people have been doing over the last 12 years or so. You have to, of course, you cannot solve this equation. You have to truncate, you make an inspired ansatz, and then again you have to substitute into the equations. You have to do all kinds of approximations, even mutilations, I would say, and then look in this truncated space for a fixed point, and then argue or hope somehow that this can be lifted to the full theory. And in fact, people do find such fixed points in various circumstances. So they have looked at higher powers of the Ricci's scalar. And the interesting result here is that if you include, say, up to 8th, I think it's 8th power in the Ricci scalar, there is evidence that there indeed is a three-dimensional ultraviolet critical hypersurface, and it remains three-dimensional. So that is somehow evidence for the second assumption which I described. Fixed points have also been found to exist for matter couplings, and they also exist in other dimensions than 4. No particular structure in the matter sector seems to be required, but what has not been done, and I think this is a kind of acid test really, or would be some kind of acid test, as I think Jack Distler was the first one to emphasize this, that you should apply this idea to the two-loop counter term itself. This has not been done because it's a very complicated calculation, and I think it's no less complicated, it would be no less complicated than the original two-loop calculation of Goroff and Sagnotti. So the open issues here are as follows. So far, there's no general argument inside that would tell us why this expectation should be true beyond this circumstantial evidence. There's the question of when you include higher order corrections, there's the question, does the theory, quantum theory, remain unitary? That's a kind of hard question to ask if you have no Hilbert space, but just something, you somehow have to find the correlators and then maybe test relations on the correlators, so that's an open question. Now another question here is that this split, the way the equation is treated, you treat these as two independent fields, but we know that at the end of the day, the result, whatever it is, should be such that the metric only depends on this combination. And when you write out covariant derivatives and so on, using this, of course, everybody knows here that this would give an infinite series, not just finitely many terms. So people have recently started looking at this and simply expanding this in terms of age, and then each of the coefficients then enters as an independent variable in your RG equation. That's quite a challenge to actually prove that this is true. There's a question about the role of field redefinitions, the covariance in field space. I just mentioned this because there's a very nice paper by Branchina, Meissner, and Veneziano where this question has been discussed. So this is a little bit about the ultraviolet divergence that we see in perturbation theory, but of course in general relativity is also the question of how would you resolve in such an ansatz the space-time singularities. Now I haven't found a very clear statement about this in the literature, but I presume it must be something as follows, namely you have to calculate this scale-dependent metric, and as you scale to large momenta, somehow the singularities must disappear. Or in other words, the hypothesis would be that this metric, somehow the space-time singularities disappear in this scale-dependent metric. So this goes back also to the question whether space-time remains a continuum to all scales below the Planck scale. And finally, if true, this asymptotic safety program must take care of not only of the non-renormalizable divergences of gravity, but it must also take care of the usual problems with the ultraviolet completion of the standard model. Standard model is generally believed in the rigorous field theory context not to exist. Landau poles and so on. So let me now go to the next item, namely canonical quantization. Now here I can flash through rather quickly because this is well known. This is the program that was initiated by Wheeler and codified somehow in the Wheeler-DeWitt equation. This is a non-perturbative and background-independent approach, but background only refers to spatial background. It is a Hamiltonian approach where you split space-time covariance, manifest space-time covariance is lost through the foliation of space and space-time into space and time. And in this view, you can think of this as being Einstein's equations or metric being a kind of dynamical system where the spatial metric evolves as a function of time according to Einstein's equations. So you can picture the cosmology or evolution of this spatial geometry in time as motion on a moduli space, namely a moduli space of 3 geometries. This is what Wheeler called superspace. The variables are, of course, the spatial components of the metric and their canonically conjugate momenta. The dynamics is defined by constraints that are multiplying shift and lapse, namely the Hamiltonian constraint and the diffeomorphism constraint. The M is the spatial index. The covariance of the theory is, of course, still there in the classical theory. It's just encoded in the Poisson algebra of constraints, which I haven't written out the indices here, but this is roughly the structure. And of course, when you quantize the theory, then of course you replace the Poisson brackets by quantum commutators, and then this is expected to be modified. So the example to keep in mind is in string theory or two-dimensional gravity, the Witt algebra, no central term, versus Virasoro algebra, which is the quantum diffeomorphism algebra. So this means that once you have a program or proposal, you must also check what happens to this space-time covariance in the quantum theory. And this is the question, what happens to this algebra in the quantum theory? So this was the program, and as you all probably know, it didn't really work out. I think by the early 80s or so, people had essentially given up on trying to make rigorous sense out of the Wheeler-DeWitt equation. And this is when this new development came with Ashtekar variables. Now, the Ashtekar variable is simply a canonical transformation from the metric variables to connection variables. And you define a connection here. So this is a spatial index, and this is a Lorentz, SO3 index. And this is a combination of the spatial spin connection plus some coefficient times the extrinsic curvature. And the extrinsic curvature is essentially the canonical momentum, canonically conjugate to the Dreibein. And what Ashtekar realized was that in terms of these variables, again, have a canonical pair of canonically conjugate variables. Namely, you take this as the fundamental variable, and the canonically conjugate variable is the essentially inverse Dreibein with a density factor, densitized triad, that's what they call it. And the other thing that got people excited was that if you put gamma equal to I plus minus I, then the constraints of the metric formulation simplify radically. So here we have a Gauss constraint. That's just a Lorentz or SO3 invariance. This is the diffeomorphism constraint, and finally this is the form that the scalar, the Hamiltonian constraint, assumes in this approach, and is much simpler than the original Wheeler-DeWitt Hamiltonian. And the other thing is that you somehow have managed to rewrite gravity in terms of a theory that lives on the phase space of an SU2 Yang-Mills theory with this field strength. So everything is expressed in terms of this field strength and the canonically conjugate variable. So people tried for a while to play with this, define some kind of connection dynamics, taking A as the variable and E to be something like D by dA. That didn't quite work. And the other thing that didn't quite work was that one had this complexity of this connection. In the classical theory, that's no problem, but in the quantum theory, you would have somehow to realize this as a quantum constraint. And this is the reason people now switch to have traded this for a real parameter, Barbero and Mirzi parameter, that's what it's called. But there's a price to pay because you lose this basic simplicity of the of the Hamiltonian constraint. So nowadays people no longer work in terms of connections and conjugate fields, but rather in terms of loop variables. So this is really the reason why people refer to this as loop quantum gravity. Namely, instead of the connection, you take the path-ordered exponential along some edge. That's the holonomy. So this is called h. And the conjugate variable to this is essentially the area. So you have some flux, and this thing is indicated by an area or some surface S. And you can easily check that these two things have very simple commutation relations. And quantization is now the question, for what variables or at what stage do you replace Poisson brackets by quantum commutators? On the previous slide, it was the connection and the conjugate variable, but now people take these as the basic variables and then quantize. Now so you can define a quantum system, and the wave functionals are now functionals that depend on these holonomies. And so they live on a spin network, which is a graph. So you have a graph consisting of edges which meet at vertices. And the wave function then depends on these holonomies of these various edges, but it also depends on intertwiners or invariant tensors that sit at the vertices. The new feature of this is that the kinematical Hilbert space can be defined. That's progress in comparison to the old Wheeler-DeWitt equation, but it is non-separable. Non-separable, well, I have no time to explain it in too much detail, but an easy way to visualize this, if you take quantum mechanics, position eigenstates, you would have this normalization. But if you replace this by the rule that x prime give 1 if they're equal and 0 otherwise, that's essentially what's happening here. But by doing this, each of these, you have an uncountable basis of states in this Hilbert space, and this is why it's non-separable. And one of the consequences is that operators are no longer weakly continuous. This means when you calculate matrix elements, then these matrix elements will no longer depend continuously on these parameters. As a consequence, if there are divergences, they will not appear in the form of ultra-wide divergences, which are squares of delta functions or something like that, but rather will appear if there are continuous sums that are formally ill-defined. And the other strange feature that we would expect a gauge theory to have negative norm states, but that's not the case here. You might think this is very strange, but there's a paper by Nonhofer and Thiering of many years ago where this is done for second quantized Maxwell theory, and they also show that you can achieve absence of negative norm states if you give up the weak continuity. So here's a picture, visualization of what quantum space-time or quantum space looks like to a loop quantum gravity practitioner. So here's a huge spin network with the edges, the vertices where they meet, and so on. So, but the essential part of this canonical quantization program is, of course, the Hamiltonian constraint. This is really where the old Wheeler-DeWitt approach failed. That was because they were not able to make sense of this constraint in a mathematically well-defined way. So here's a short summary of what happens in loop quantum gravity. So you first have to solve the diffeomorphism constraint. Now that was the easy thing in the old Wheeler-DeWitt approach. They would simply look at formally spatial diffeomorphism invariant functionals of the 3-metric. This cannot be done here because these spin network wave functions are much more singularly supported. So you define this simply, you impose diffeomorphism invariance by simply doing a formal sum over all diffeomorphisms. Now you might think this is a really strange thing to do because this is really formal. Does this make sense? And the answer is yes, actually you can make sense of it if you think of this thing no longer as a state in the Hilbert space, but as a distribution. And this is because this by itself, this makes sense when you sandwich this or take scalar product with a spin network wave function, because then this continuous sum will collapse to a finite sum or even only just one term. So this is a general way to get distribution spaces, starting from Hilbert spaces. You look at dense subspaces and look at the dual, which is then bigger, and the distribution space. Now the main success, as in comparison to Wheeler-DeWitt, is that now a Hamiltonian can be defined formally, a regulated Hamiltonian. And I have no time to describe this in detail, but many of you may know about the old Mikdal-Makayenko approach to gauge theories, where everything is done in terms of Wilson loops, and you have to express the field strength in terms of holonomies. So this is what's being done here. Let me see. Well, you see the Hamiltonian is this, so this piece has to be done from the holonomies, but you also have to recover this piece, and this is what this term here does. So this is the holonomy, and then here you have something called a kinematical operator, which is called the volume, that can be defined. Its action can be defined on a spin network. Now this is a rather more ugly term, which appears if gamma squared is not equal to -1. So we can discuss it afterwards, but this actually you have to, this is the extrinsic curvature, and this itself has to be expressed as a multiple Poisson bracket or multiple nested commutator of the basic variables. So the proper definition of this Hamiltonian on these states can now be in principle defined, but it's subtle, because if you act with this thing on some spin network wave function, and then you also need to take this epsilon to 0, then the resulting states runs to an uncountable sequence of mutually orthogonal states. So at best you can make sense out of this as a weak limit. So what does it do physically? Well, what it does, it sort of acts on a spin network vertex by inserting a plaquette. I call this, you sort of take the spin networks and start adding spider webs to it. So you can picture the action of this, but it's only the action of the first term. And furthermore, it acts spider webs that are infinitesimal, because you have to shrink them to 0. So this is an ultra-local action in some sense, in the sense that the Hamiltonian doesn't connect different vertices of this spin network wave function, but this is only something very local. This is why even in the loop quantum gravity, the doubts have been raised as to whether this is really a good Hamiltonian. It is, when you try to work with it, and we've done so, just try to take a simple example of a spin network, a Mercedes star or something, it's extremely cumbersome to evaluate. And there are hidden ambiguities in this definition beyond the usual ordering ambiguities. For example, there are different definitions of what this volume operator does. There are also different ways, question of how you insert this plaquette into the spin network, that's somehow hidden in this prescription, but which should keep in mind that this is highly ambiguous. So these spin network wave functions, they're mathematically well defined, clearly, but they're very hard to interpret, because if you think about recovering the metric operator in this formalism, in the connection formulas would be a singular second-order functional differential operator, but then here it's even worse, because you somehow would have to express it in terms of holonomies. Space-time covariance, now this is also a somewhat murky issue, because you treat the constraints in very different ways. One solves the diffeomorphism constraint formally, and then one has a habitat of states on which the action of the Hamiltonian is defined. But if you don't choose the right habitat, and this is some further modification I have no time to talk about, you must make sure that this action doesn't throw you out of this habitat, so you cannot act another second time with the Hamiltonian. So there's some elaborate discussions of this in the literature, but it all boils down to that the best you can show, you cannot evaluate this commutator as a bona fide commutator with some operatorial expression as the explicit result. Well, there are numerous, and I personally would think that the very different treatment of the constraints make the space-time covariance of the effective low-energy theory doubtful. Well, there are all kinds of ambiguities. So this is basically the status. There's some maybe some modification here and there of some technical nature, but most people here in this field have now moved on the one hand to loop quantum cosmology, on the other to covariant approaches, spin forms, which is something I want to tell you now about. This is a covariant version of the canonical theory in the sense that you now look at the evolution of spin network functions in time. So here's the spin network. I'm not sure if you can see it. So you add these spider webs, as I said, and then space-time pictures like this. And the spins, which were attached previously to the links, are now attached to the surfaces. And the intertwiners previously associated with the vertices are now on the links. I should like to emphasize that the link between loop quantum gravity and spin forms only exists at the kinematical level. There's no rigorous derivation of this. It's at best heuristic, I would say, and I think it's a better way to think of spin forms as novel models of lattice gravity. So here the aim is now to emulate in a rigorous way the formal path integral of gravity. Here in old-fashioned quantum gravity, one would like to calculate the product, scalar product between two metrics. So think of a space-time slab and metric on top, spatial metric on bottom, and something you integrate between all metrics in between. And here what you do is very similar, but you connect the two spin networks by a spin form. And then you have the usual composition rules, and the physical transition amplitude should be something like a sum over all forms, whatever that means. Now, so here, what one has here is some kind of amplitude that is the analog of this exponential of I action. But what is this? So to arrive at candidate mathematical expressions for this, people start from what's called BF theory. So this is purely topological theory. Here's the connection. Here's the Lagrange multiplier. And this works beautifully in 3 dimensions where gravity is topological. But in 4 dimensions, gravity is not topological. And therefore, this has to be, you have to impose a constraint that tells you that this is really a product of 2 vierbeine. So this is the starting point, and then you perform a procedure to get this spin form amplitude. And the procedure as follows. You first discretize this BF theory on a simplicial complex. Now, the simplicial complex is something that's dual to the spin form in the following sense. If we have a triangulation of a 4-manifold, then each 4-simplex, you put a vertex at the center, and the boundary consists of 3 simplices connecting to another 4-simplex, and then you link the vertices of the 2 4-simplices by an edge, and that's the spin form edge, and so on. So there's a dual description of the spin form in terms of a simplicial complex. Well, I think I will skip this a little bit, but at the end of the day, you arrive at the following expression for the spin form partition function, where you associate amplitude factors with the vertices, the edges, and the faces. Depending on the dimension, you get higher J symbols. In 3-dimensional gravity, you just get 6 J symbols, but in 4 and 5 dimensions, you would get higher dimensional expressions, or higher dimensional generalizations of these multi-J symbols. So, there are various questions here. I think I have no time to discuss all of them, but certainly one question that always comes up, and I always keep asking, and I never quite get a satisfactory answer is this spin form now the actual quantum space-time, or is it something that I should take a refinement limit of, or how should I perform this sum? There are various technical issues. How much time do you have?
15 minutes.
Okay, so still some time. And of course, the unsolved question, just like in the canonical program, is how do I get out of these discrete objects? How do I get a continuum space-time? And how do I get in such a way that finally, in the long-distance limit, if such a limit can be defined, how to get Einstein's equations? There are various technical issues here, also to do with the fact that one in this partition functions, one has to sum over all spins. So this introduces potential divergences, and depending on the models, it's either divergent or not. But there are some models for which it is convergent. There are numerous ambiguities, valences of spin form vertices, choice of amplitude factors, treatment of simplicity constraints, and of course not to mention inclusion of matter couplings. But the hope, when you confront the practitioners of these approaches with this ambiguity question, they always express the hope that actually it doesn't matter how I triangulate the manifold, there will be certain universality classes, and then all these ambiguities will be reduced. So there are some open questions, and a further development that sort of tries to answer at least some of these questions is group field theory. And here the aim is to reproduce the spin form amplitudes, which I've shown you before, or interpret them as Feynman graphs of an abstractly defined field theory. Abstractly defined field theory means it's a field theory that doesn't live on space and time. There is no space-time. It lives on a group manifold. And the fields are functions of group variables whose number depends on the dimension. And rather than to explain these details, I just show you the following picture. This is the picture for three-dimensional space-time. If you triangulate a three-dimensional space-time in terms of three simplices, that means tetrahedra, the spin form vertex sits at the center of this tetrahedron, so it's dual to this tetrahedron. The links of the spin form are dual to the faces of this tetrahedron, and finally the faces of the triangulation are dual to the links, the faces of the spin form are dual to the links in 3 dimensions of this tetrahedron. So because in the spin form, picture, the spins are associated with the faces. In this triangulation picture, they're associated with these links. So you have a tetrahedron, and you put spin on each link. Now, if you look up the definition of 6J symbols, say in Landau-Lifshitz, then you will see that the 6J symbols are always associated with such a tetrahedron, because the spins have to satisfy this inequality, triangle inequality. And then you see how, if you take this apart, how you can decompose or reinterpret the triangulation in terms of this group field theory picture. So the tetrahedron consists of 4 faces, but each faces comes with 3 links, so with 3 of these SU3, SU2 variables. And finally, then you have to connect them in such a way, so the faces share one spin, so that's expressed by this, by linking them in this particular way. And then you have this object here you can think of as some kind of propagator. So that is a sort of field theoretic description of how to generate a triangulation in some kind of a field theory. So this is the 3 simplex, this is the vertex, that's with the 3 faces making up this tetrahedron, and here's the propagator. So you have the field theory is then essentially a free term plus an interaction vertex, and the interaction vertex encodes precisely this picture. Now the big nice thing about this is that previously I said I don't know, should I sum, refine, whatever. This sum and the expansion Feynman graph produces precisely the diagrams. Each new term in higher order adds something like a new simplex into this triangle, this simplicial decomposition. So this prescription, the nice thing about this is that it automatically defines for you the sum of all spin forms. And the idea is here that you have defined something like a quantum field theory, but the quantum field, the quanta of this field theory have quanta of space and time, or space-time. So that's why some people say that this group field theory can be thought of like a second quantization of loop quantum gravity. There's a lot of development going on at this time. People doing this are very enthusiastic. And I should say they go back to older ideas. You're all aware of this link between strings, matrix models, planar QF quantum field theory, but this is like a higher dimensional generalization. So that's very nice to have a field theory, but in some sense we've now come back to square one. Because how is this theory defined? This theory is defined as a perturbation theory, just like, phi to the fourth theory in standard quantum field theory. So we're somehow back to the beginnings of quantum field theory, and talking to these people, I get the impression this is like quantum field theory in the 1940s. People didn't quite know what the rules were, how to find the good models, what are the principles, the guiding principles for constructing such field theories. And furthermore, you notice here renormalizable, this thing again has divergences, which you can think of being related to the sums of the spins in the spin foam picture. So you have to check that it's renormalizable in the sense that at each order, when you do these quantum corrections, you must not introduce new kinds of vertices. So it seems like this is a subject that is very beginning. As I told you, the ones I've talked to, are very excited about this, especially about this aspect, I should say, that there's some quantum theory where the basic quanta are quanta of quantized triangulated space-time. But another thing that has not been solved here is the question of matter couplings. They're only known for 3 dimensions. With point particles, we understand point particles, 3-dimensional gravity, they just there are no gravitational waves, they just lead to defect angles and such things. But it's not known how to do this for 4 dimensions. So when I ask how would you put a Dirac fermion in this context, people don't know. In fact, I get the impression that it's quite awkward if you try to do this. So I would like to end with some general questions. All these approaches emphasize background independence. And the question here is really how much background independence do we really need? Is it, like we have to, in the quantum gravity, completely dispose of any kind of metric background? Or is it only possible to formulate or define the theory in some kind of background? Like asymptotic safety, you take some background and you just check covariance with respect to this background, but which background to choose is up to you. And the second question, is really possible to quantize a theory in terms of gauge invariant variables only? And this is something that doesn't seem to be possible in ordinary quantum field theory, if you think about this Migdal, Makayenko, Polyakov approach of many years ago. So, well, I looked up in Wikipedia what is the definition of background independence. You may not be able to read it, so let me read it. It says, background independence, also called universality, is the concept or assumption fundamental to all physical sciences that the nature of reality is consistent throughout space and time. More specifically, no observer can, under any circumstances, perform a measurement that yields a result logically inconsistent with the previous measurement under a set of rules that are independent of where and when the observations are made. I think that clarifies it, doesn't it? Anyway, for us, it simply means that the proper formulation of quantum gravity should perhaps not depend on a given space-time metric or any other background data. Well, that's what people have been looking for a long time in string theory, and it seems very hard. And I just include this picture because it seems like when at LHC, when we do calculations in QCD, yes, there's gauge invariance, but whenever you calculate something concrete, you have to use gauge variant variables, get the gauge field itself, propagators, and so on. And only at the end of the calculations do you check or verify that the theory or the result is really gauge invariant. So, oops. So there are more questions also to do with the question of what you call regularization versus renormalization. I'm having debates with these people because I say that what you do is just a regulator. It's not, and if your result depends on the regulator, that's not a good starting point. So far, in all these approaches, there's no indication whatsoever that matter of any kind may be needed for consistency of quantization of gravity. In particular, these approaches cannot reproduce, for the time being, the consistency requirements that we know from the standard model, like anomaly cancellations of the standard model fermion multiplets. The question of continuum limit and also semi-classical limit, h bar to 0, remains unsolved after many years, despite quite some effort. And this is, of course, also related to the question, if you have such an abstract spin network and no length scale, how do you actually introduce it? In normal lattice gauge theory, we know how to do this. We start calculating with dimensionless quantities, and then we put in the scales and let the theory scale to a point of phase transition. But the question is here whether these theories really exhibit such things, phase transitions and so on. And then this question is, of course, which is the right spin foam or group field theory? Are there any kind of principles like symmetry or other guiding principles that would tell us which is the right model? So my last transparency. I want to summarize this, but this is a very personal view. Many people from that community perhaps certainly will not share everything here, what I say. But let me first say that there are now many, I would say, interesting, intriguing, like this idea about quanta of space-time, innovative proposals for a non-perturbative description of quantum space-time and quantum geometry. You see, this is something that string theory at the moment doesn't really provide for you. When you ask someone, what does space-time look like at the Planck scale in your theory? That's a kind of hard question to answer, but here at least we have some proposals for doing such a thing. There are many similarities between these approaches, and there's also in the terminology. Some people, when you say loop quantum gravity, they really mean not just the canonical program, but this whole set of ideas. It's all somehow connected, but the similarities are mostly at the kinematical, at the level of kinematics. And when you start asking questions of how you define the dynamics, then they're wildly diverge, I would say. So there's absolutely no convergence of ansatz and ideas, at least so far. Even though from the outside it looks, some of these things look very similar. Now again, to make this point again, complete background independence, by which I mean you really try to work without a background metric, not just in kind of background covariant formalism, invariably entails difficulties in recovering the classical limit. And these difficulties have not been resolved in 25 years of work. And as long as you cannot recover the classical limit, of course, you can also not say what is the fate of the two-loop divergence. Now this point, I think if I was working on this is the point that would bother me most. This number 10 to the 500 is really meaningless, but string theorists love it, and that's why I put it here. The ambiguities are here of such a kind that if you look very closely as to what the models are and possibilities are, you have a large number of quote-unquote consistent Hamiltonians, consistent spin foams, consistent RG flows. And sometimes when I sit in these talks and listen to this, I think it's working too well. I'm almost finished. It would be better if they found some inconsistency to rule out certain possibilities. So this fuels the suspicion that the non-predictivity is really just the old non-renormalizability of perturbative quantum gravity, but in a different guise. So I don't know how one would somehow discriminate between these possibilities, but certainly confirmation and refutation by experiment and observation for these ansatz seems even more of a challenge than it is for string theory. Thank you.
Okay, Ed.
I have a very quick comment and question.
The comment is that where we actually have some success at finding background independent formulations is in the ADS-CFT duality.
Yes.
And the question is this: people who work on asymptotic safety, do they generally, I don't have any intuition about the physics of the hypothetical critical point. So is it supposed to have global violent variance or local violent variance, or what?
Global, or, well, I think that, no, that question is not answered in what I showed you, but talking to some of my colleagues at my institute, they're trying to work with a more general ansatz, and they think they find some evidence that actually there is a distinguished fixed point, and the fixed point is just Weil gravity, r squared. I mean, the Weil invariant theory in 4 dimensions. That's, which I think is, at least a little bit plausible.
Yes.
When you were talking about asymptotic safety and you mentioned fixed point, it's actually a little bit surprising, because I was always thinking that the presence of the fixed point is something happens when theory is renormalizable, but gravity is not renormalizable, so why is there a fixed point?
No, but the fixed point is supposed to be there not at vanishing coupling, but somewhere for non-vanishing coupling. And it's a little bit like this non-trivial fixed point that you also have in the ON sigma model in 3 dimensions. Or another example that's often mentioned is the Gross-Neveu model that also looks non-renormalizable, but still they can make sense of it. So this is in a similar spirit. But
Okay, I'd like to say something here. You mentioned in the beginning, Hermann, that there is some result of Ashok Sen actually.
About what?
You mentioned about some results on black hole entropy by
Ashok Sen.
Ashok Sen. So
Well,
may I
Ashok
invite
here?
him actually to make a statement about the very sharp result that he has obtained, which is not consistent with calculations in loop quantum gravity. Ashok, where are you?
Ashok, why don't you comment?
Well, I think there is disagreement in the loop quantum gravity community as to what they have calculated. I mean, if they claim that their result is not the complete answer, then of course there is no disagreement. All that I wanted to say is that whatever result they have got is not what you get from the low energy physics. And so if that is the complete result, then there is a clear disagreement.
Last question.
Obstacle for this method when there is a supersymmetry. For example, supergravity.
Yes, that's so. The question is, what can you do with? Can you make these unsets supersymmetric? Indeed, actually, this was the reason I was initially intrigued, at least by Ashteka's variables. When you rewrite 3-dimensional gravity in terms of canonical formalism, it turns out that actually Ashteka's variables are very, very nice. I mean, they facilitate these calculations of canonical brackets, and the reason is that the Ashteka variable is precisely the pullback to the spatial hypersurface of the 4-dimensional spin connection. And I always say that if people in 1979 had really pushed canonical gravity all the way, they would have discovered Ashteka's variables. So that's possible. But what is not possible and has not been done, as far as I know, is actually going beyond the kinematics and rewriting the supergravity theory, going beyond the rewriting and actually looking at quantum supergravity. That's not been done.
Okay, I think